Welcome back. In this video, we're going to continue learning about chemical reactions. We'll review the 4 driving forces that are involved in aqueous exchange reactions, and then we will use the solubility guidelines in order to predict whether or not a precipitate will form. We'll identify spectator ions and then write out the complete ionic and net ionic equations. So in previous videos, we looked at how there are 4 main driving forces that will dictate whether or not a reaction occurs. For displacement reactions, we can have either redox reactions that occur, which are most commonly occurring in the single displacement type reaction. And then we can have the formation of a precipitate, weaker non-electrolyte, or gas. In this video, we're going to focus on the formation of a precipitate. So in a previous video, I mentioned somewhat jokingly that in chemistry, we might say that if you're not part of the solution, you're part of the precipitate. And this is true. We can use the solubility guidelines in order to predict whether or not a substance will be part of the solution or whether it will form a precipitate. So let's go through these different guidelines. Ammonium salts and salts that are alkali metals, or in other words, group 1A, these always form soluble compounds with water. In other words, if you have ammonium combined with any other anion, it's going to be water soluble. If you have potassium with any other anion, it's going to be water soluble. Similar, there are a certain set of polyatomic anions that are always soluble. Nitrates, perchlorates, and acetates are always water soluble. The halides, chloride, bromide, and iodide, these tend to be water soluble. However, there are some important exceptions. Mercury, silver, and lead combined with chlorides, bromides, and iodides are actually insoluble. So let's take a look at an example of this. If we have lithium chloride, that will be soluble, and therefore we would label it as AQ, aqueous. However, if we had silver chloride, that would be insoluble, and so that gets labeled as a solid. The last polyatomic ion that tends to be water soluble is sulfate. Most sulfates are soluble, and the exceptions that you need to be aware of are calcium sulfate, strontium sulfate, barium sulfate, and then mercury, silver, and lead sulfates. Now, you don't need to have these memorized because they're given to you on the data sheet that we provide you in the ebook. Now, there are a certain set of polyatomic anions that tend to be insoluble. Those include carbonates and phosphates, and the only exceptions to those are these exceptions that are listed here. So ammonium in the group 1A. We also have hydroxides and then the monoatomic anion sulfide, which tend to be insoluble. And the exceptions there are the ammonium ion, group 1A, and then calcium, strontium, and barium. So these are the solubility guidelines, and we can use these to predict whether or not something will be a precipitate. And again, these guidelines are found for you on your data sheet. Let's try a practice problem. Which solution would form a precipitate when mixed with a solution of bismuth bromide? I'd like you to pause the video and try and determine this on your own using the solubility rules, and then I'll walk you through a solution. All right, so the first step to solving this problem is actually to identify what the products are for each mixture. So we have in the first combination, barium hydroxide and bismuth bromide. And for all of these reactions, we're doing a double displacement. And so the cations swap places, or we can think of it as the anions swapping places. That means then In beaker A, we would have a combination, the products of this would be bismuth hydroxide and barium bromide. In beaker B, we swap bismuth and lithium. So we have lithium bromide and bismuth perchlorate. And then beaker C, we have bismuth switching out for lead. So we have bismuth nitrate and lead bromide. Now let's evaluate for each of these products, which of them are soluble and which of them are insoluble. So for the first one, bromides are mostly soluble. Notice here the only exceptions are silver, mercury, and lead. So bismuth bromide will be soluble. However, hydroxides are mostly insoluble. The exceptions to that do not include bismuth. So bismuth hydroxide is going to be a solid. For the second solution, all lithium solutions are soluble. All perchlorate solutions are soluble. For the last solution, nitrates are always soluble. However, lead is one of the exceptions for bromides. Therefore, lead bromide is going to also form a solid. Let's now turn our attention to actually writing out the chemical equations. So the chemistry that's actually happening can be expressed in what we call a net ionic equation. And this shows the ions and or molecules that are directly involved with the reaction. And we eliminate anything else that we call a spectator ion. In order to determine the net ionic equation, we first must write out a balanced molecular equation. When you're writing out a molecular equation, you need to make sure that you can predict the products properly and that the charges match up. So let's say that we have lead nitrate and we mix it with potassium iodide. What would we make? You should recognize that this is a double displacement reaction. We have two compounds, and so we swap the locations of the two cations or the two anions, and we would see that we would form lead iodide and potassium nitrate. Notice here I've indicated lead iodide as a solid. Looking at the solubility rules, you should recognize that lead iodide would be insoluble and therefore a solid, but potassium nitrate would be aqueous. Now we need to make sure our charges are matched up. Nitrate has a charge of -1, and there are two of them, which means our lead must have a +2 charge. Iodide has a -1, potassium has a +1 charge. Therefore, when iodide reacts with lead, it balances out with 2 iodides for every 1 lead. And therefore we have a coefficient of 2, or a subscript 2. For potassium and nitrate, they're both a magnitude of 1, +1 and -1, so those are balanced out. Then make sure that your chemical reaction is balanced by accounting for the coefficients. Because we have 2 nitrates here on the left, we must have 2 nitrates on the right. Now we've affected the number of potassiums. So we have 2 potassiums on the right, and we must have 2 potassiums on the left. At this point, everything should be balanced. Pause the video and verify that now. Welcome back. Now that we've determined that our molecular equation is balanced, both in terms of the charges and in terms of the number of each atom, we can move on. What we need to do now is apply the solubility rules and dissociate any strong soluble electrolytes. And this will allow us to write the complete or full ionic equation. So anything that is a solid, liquid, or gas is a non-electrolyte and does not dissociate. Also, anything, we can have some aqueous components that are also non-electrolytes. If we have molecular aqueous components, those are also going to be non-electrolytes. That would include something like sugar or molecular iodine. And so you need to be able to differentiate between our strong electrolytes, which are listed here, which are made up of ionic compounds, and our non-electrolytes, which include ionic compounds or molecular compounds that are solids, liquids, and gases, or that are aqueous but are made up of covalent bonds only. So we dissociate the lead nitrate, the potassium iodide. The lead iodide stays together because it's solid, and we dissociate the potassium nitrate. Now we can identify our spectator ions. These are ions that appear on both sides of the equation. So all you do here is take a look at which substances are the same. And you can see that we have 2 nitrates that are both aqueous, and we have 2 potassium ions that are both aqueous. All of the other substances change. We had lead and iodide, which were aqueous and now have become solids. So they've participated in the chemical reaction. After we've eliminated the spectator ions, we rewrite the equation, and this gets us our net ionic equation. And if we were to identify the driving force here, it would be the formation of a precipitate. That's it for this video. Thanks for watching. Have a great day.